Thank you for the introduction. This is a joint work with Professor Ohad Ben Shachar, which started out at the Interdisciplinary Computational Vision Lab at Ben-Gurion University and is now the basis for a university spin-up startup called HC Vision. And what we're doing is snapshot imaging with low-cost sensors that gives us hyperspectral data in the case of RGB sensors in the visible and near-infrared frequencies, and obviously we can go to other areas as well. Now, fortunately, you just got a very good primer on hyperspectral imaging, what it is, what it's good for, and why you might want it. But as you can see, the equipment that you need and the processing that you need is quite complex. So just a quick rundown to get us back to where I want to be. Monochromatic sensors have a single spectral band. You get only brightness information. If you go to RGB cameras, you get 3 spectral bands, RGB. After RGB sensors, you'll find multispectral sensors, which often have several spectral bands, usually with some sort of filter wheel system, but not exclusively. And finally, we have the type of camera that we've been talking about since this morning, hyperspectral cameras that can give us a wide range of narrow bands and a lot of information, but they need to do some sort of scanning in order to get that information. And this information is quite useful. We've already talked about that quite a lot. There are many industries that are using this information and a lot of exciting applications, but you'll find that consumer applications are almost non-existent. We don't see this coming to the consumer market, and I'd argue that that's because these hyperspectral cameras are very expensive, they're very bulky, they're complex to operate, they need to be in a stationary position. It's not something that you can carry around in your pocket and use during your day-to-day lives. So at the moment, the applications are really limited to industrial high-cost settings. And one of the things we're looking to do at HC Vision is bring these applications to the consumer market. So let's have a look at the various acquisition tools that we have at the moment. If we look at spatial resolution and spectral resolution, we'll find monochromatic cameras have a very high spatial resolution, but a spectral resolution of 1. RGB cameras are close behind the monochromatic cameras. We give up a little bit of spatial resolution with a Bayer filter, for example, in order to get a little bit of spectral resolution. On the other far end, we find spectrometers, usually laboratory equipment that will give you a point measurement, but a very detailed spectrum, but just for 1 point. So basically a spatial resolution of 1 and a very high spectral resolution. Traditional hyperspectral imaging systems, like the type we saw in the previous talk, will have a very high spatial resolution and a very high spectral resolution. That would seem ideal, but that comes at the cost of scanning. Modern hyperspectral systems try to do a trade-off. They will give up some spatial resolution and some spectral resolution in order to get faster acquisition and maybe give up scanning altogether. For those of you familiar with it, SIO, it's a nice product by Consumer Physics. It's a consumer-level handheld spectrometer, very similar to a laboratory spectrometer, just lower spectral resolution and very low cost. We're aiming to come in right about here, match the spatial resolution and the spectral resolution of traditional systems. But, well, we already have traditional systems. Why would we need another product? So the truth is that this is only part of the story. If we're looking at resolution, we also need to be looking at acquisition speed. We need to be looking at the time dimension. And if we take all these cameras and move them to this side of the graph, we find that traditional hyperspectral imaging systems have a very low acquisition speed. You might have seen in the previous presentation, we're talking about hundreds of frames per second, but that's per line. If you want to get an entire image, you need to scan spatially. So you have a big acquisition speed problem. Modern systems give you better acquisition speed, but at the cost of resolution. So again, what we're trying to do is get snapshot images, almost instant acquisition, with a high spectral resolution and a high acquisition speed. And where we are at the moment, we have a prototype test rig, which uses a 4-camera setup. We've demonstrated the technology on a single camera, single sensor setup, and we are combining these two at the moment in order to produce a low-cost, low-weight, chip-based solution that can be integrated into a variety of platforms. And what I'm here to tell you about is how we're doing that and why this is even possible. And to do that, let's take a minute to talk about projection. Camera sensors, as you're all familiar with, are two-dimensional. We have a two-dimensional sensor surface, and we're trying to image a three-dimensional world. Now, this forces us to use some sort of projection, usually done by a lens. So you have three-dimensional information projected to a two-dimensional space, and that's what we record. This is obviously not news to anyone in this room, but if we look at the spectral dimension, something very similar is happening. We have spectral information, we have light at a large variety of wavelengths coming into our camera sensor, and it is projected to a small amount of measurements. If we're looking at an RGB camera, that infinite dimension spectra is projected to only 3 measurements. Now, for the sake of this talk, I will look at spectra as if it's a 30-dimensional space, which is a good sampling rate for visual spectrum. So we have a 30-dimensional sample, which is then downsampled to 3 dimensions. And what we want to do is reverse that. We want to take this 3-dimensional measurement and go back to a multi-dimensional source. And that's quite difficult, but as you've seen, it's not impossible to reverse the 3-dimensional to 2-dimensional projection of space. Why can't we reverse this 3-dimensional projection of hyperspectral data? So the limitations we need to overcome are, first of all, the many-to-one mapping. We have a 30-dimensional space projected to a 3-dimensional space, which mathematically is impossible to reverse. But fortunately, the real world adds some constraints, which we'll see in a moment. The second constraint, and the more important one, is the response of the sensor we're targeting. Obviously, if a stimulus does not produce a sensor response, I will have no way of detecting it. But if we look at what an average RGB camera can see, it will respond usually to stimulus between 400 and 900 or even 1000 nanometers. So anything the camera can see, we have the potential to reconstruct. And now the question is, how can we do that, and how well can we do it? So to answer that question, we collected a large database of natural hyperspectral images. Now, natural images are the type of scenes that you'll see in your day-to-day lives. These are the images that you'll find on your phone, as opposed to airborne images, laboratory images, production line images. These are things you'll see in your day-to-day life. And this is the setting where we want to work. This is where we want to do our reconstruction. So we collected a very large database of these hyperspectral scenes using a hyperspectral camera. This is, by the way, available online for research if you'd like to have a look at the data yourself. And we started analyzing this data to see if what we want to do is possible. And we found some very interesting things. First of all, if you look at the effective dimensionality of the hyperspectral data we collected, we find that instead of having 30 dimensions, its effective dimension is about 5. That means that if we do principal component analysis, the 5 first principal components will account for over 99% of sample variance. So we lowered the dimensionality problem from 30 to 5, which is great, but we haven't quite gotten to 3 just yet. Another interesting observation is that if we look at the mapping, if we look at all the spectra samples that map to a specific RGB value, a single RGB value, and we compare them to all possible theoretical spectra samples that would map to that same RGB value, we find that the samples we've actually seen occupy a very low dimensional manifold within the space of all possible spectra. Now, this is a single RGB value, but we find that this is repeated over every single RGB value we test. So natural spectra occupy a very low dimensional manifold of the theoretical space from which these spectra are sampled. So we're getting to be a bit more optimistic as to our ability to guess which spectra corresponds to a specific RGB value. And if we continue to dig into this data, we find a few more interesting things. First of all, distance in RGB space and in hyperspectral space is highly correlated, meaning that if we find two RGB values that are close to one another, they are likely generated by hyperspectral samples which are, again, close to one another. Meaning that if I make a small mistake with an RGB measurement, I will likely make a small mistake with the hyperspectral data that corresponds to it. And again, if we look at all the spectra samples that match a specific RGB value, and we take the mean of those samples, you can see that here, the blue line, that's the mean of all the spectra samples that matched one RGB value. And then we look at the standard deviation, we find that the standard deviation is quite small relative to the mean. So again, if we're looking at all the spectra samples in nature that map to a specific RGB value, we find that there isn't a lot of variation. Now at this point, you could say that if we had a camera crafted with 5 filters that match the principal components of the data we want to collect, we could accurately collect hyperspectral data. But that's not good enough because, first of all, we'd like to use less than 5 filters, and secondly, the principal components are not very easy to implement as optical filters. It's not something you can just create a coating for. So principal components aren't good enough. Another approach we could take is, well, if we record every single spectra that we're likely to see and its corresponding RGB value, and we take averages of those values, if we match an RGB value to the average spectra that would have generated it, that would also give us a pretty good approximation. But again, that's not a practical approach because we can't collect every single spectra sample in the world, and even if we could, the database that would result would be enormous. So we are beginning to get a feeling that it's possible to do this reconstruction, but it's not easy. So we're trying to find a workaround, a way to reduce the dimensionality even more so that the reconstruction could be possible. And in order to do that, we went to overcomplete dictionaries. Now, I'm assuming that most of you aren't familiar with this, so I'll give you a quick primer. Hopefully, a lot of you are familiar with wavelet bases or cosine transform bases, and we use these to represent spatial images, and we find that the wavelet base is very good for images with sharp edges, while the cosine transform base is great for images with smooth gradients. And if I want to represent an image efficiently, choosing the right base will allow me to do so. But what happens if I don't know what type of image I'm going to represent? I could pick the wavelet base for a smooth image and then I'd get a very bad result, or I could pick the cosine transform base for a sharp image and get a bad result. And the solution to this is quite simple. We can take these two bases and combine them, and taking from this new dictionary we've created, we can then represent an image efficiently using only a small amount of vectors from this base. So we add a small text to the size of our representation and get a much more efficient and generalizable representation. How do we apply this to hyperspectral imaging? Well, we take a spectra sample and create an overcomplete dictionary that can efficiently represent our spectra samples. So each sample can be decomposed into a small amount of what we call dictionary atoms, a small amount of vectors that will accurately represent that sample, similarly to principal components, but using less components. So instead of getting 5 components to represent each sample, I could use 3 or even less. And what we found is that this conversion, you could say it survives projection to RGB, meaning that these components that compose each spectra sample have corresponding RGB values which we can locate in a new image. And if this is not entirely clear at the moment, let's have a look at the pipeline we've constructed, and hopefully that will clarify things a bit. So let's take a step back and go over our reconstruction process. We take a large amount of hyperspectral images, create a very small overcomplete dictionary. We're taking 2 terabytes of data, breaking them down to less than 1 megabyte. And this dictionary is then projected to RGB, where we have a camera-specific dictionary, each sample corresponding to its RGB value. Given a new image, we can then create we use our camera-specific dictionary, find a representation using this dictionary, and apply it to the hyperspectral dictionary. This gives us our hyperspectral estimation, and I'll skip this because we're short on time. And we find that that gives us a very good estimate. On the left here, you can see an experiment. These are the ground truth data images for each wavelength, just a few from the entire spectrum. These are the reconstructions. Here are the error maps, which are quite shallow. On the right, you can see single pixels reconstruction versus ground truth, so we can accurately represent the nuances of different spectra samples. And over the entire data set, we find that the accuracy over hundreds of images exceeds 90%. We have very good reconstructions over a wide variety of scenes using a single dictionary. Now, one last trick I'd like to leave you with is the use of this methodology for improving sensor quantum efficiency. And this is actually the first product that we're pushing out of HC Vision. Instead of acquiring images with RGB filters that are not very light efficient, you're using about 30% of the incoming light when you apply an RGB filter like this. We use specially crafted filters that allow over 100% more light to reach the sensor. Now, doing that, you obviously lose color accuracy, but then you can reconstruct the spectra of each point and project it to RGB, resulting in an image that is significantly brighter and just as color accurate as your original RGB camera. So that's just a taste of what we're doing in HC Vision. If you have any questions, I'd love to take them now, or you could contact me online or offline. Thank you very much.